Good day, the topic is frictional or skin resistance Q sub S in sand. So for the general method, the unit skin friction increases with depth more or less linearly to a depth of L prime and remains constant thereafter. The magnitude of the critical depth L prime may be 15 to 20 times the pile diameters. A conservative estimate would be L prime is approximately equal to 15 times D. So as presented with figure 3.27. So the skin frictional resistance of a pile or Q sub S is equal to the sum of P times delta L times F. Again, P is the perimeter, delta L is the segment length, and F is the unit friction. So for Z, that is equal to 0 to L prime, F is equal to K times sigma O prime times tangent of delta prime. So take note that for F, for 0 to L prime, get the average. And for Z that is equal to L prime to L, which is already constant, F is equal to the F at Z that is equal to L prime. Again, K is the effective earth pressure coefficient, sigma O prime is the effective vertical stress at the depth under consideration, and the delta prime is the soil to pile friction angle that is approximately equal to 0.5 of P prime to 0.8 of P prime. So the table presents the different values of at rest pressure coefficient for different pile types, or otherwise our K sub O. So according to Mansur and Hunter, the average values of K are, so we have H piles, K is about 1.65, steel pipe piles, K is about 1.26, precast concrete piles, K is about 1.5. So for Coyle and Castello's method, they proposes for Q sub S, which is equal to F of times P times L, wherein our F of is K times sigma O prime bar times the tangent of delta prime, and multiply it to P times L, where our sigma O prime bar is the average effective overburden pressure. The delta prime is the soil pile friction angle that is about 0.8 of P prime for Coyle and Castello's. For K, that is the lateral earth pressure coefficient. So from field observation, we may use figure 3.28. So for the variations of our K. So take note that if the line or the curve is not available for a certain angle, consider only within the range of 30 degrees to 36 degrees. So apply interpolation for two notable values of your K. For example, if P prime is about 31.5 degrees, then interpolate the results for 31 and 32 degrees. And if the angle of friction and the embedment ratio is or are out of the range, then do not use the method to avoid errors. So thus for this theory, Q sub S is equal to the K times sigma O prime bar times the tangent of, updating now our delta prime as 0.8 of P prime times P times L. So for our sample problem, so consider a 12-meter long concrete pile with cross-section of 0.4 meter by 0.4 meter fully embedded in sand. So for sand, unit weight is 17.6 kilonewtons per cubic meter and soil friction angle is 30 degrees. Estimate for letter A, the frictional resistance Q sub S using K equal to 1.3 and delta prime as 0.8 of P prime. For letter B, the frictional resistance Q sub S using coil and Castellius method. And for C, the ultimate and allowable load if the factor of safety is equal to 3 and assume Q sub S is the average of letter A and letter B requirement. Consider Q sub P, which is the average of the three methods. So from our previous discussion, that is equal to 670.095 kilonewtons. So for general method, K is equal to 1.3 and delta prime is equal to 0.8 of P prime. So determine the depth wherein the unit scale friction, or F, is increasing and remains constant. So at L prime, wherein L prime for conservative condition is about 15 times D, wherein D is our side dimension or side size for our square pile, that is about 0.4 meter. So L prime therefore is equal to 6 meters. So with this value of L prime, we need to determine the value of unit friction that is increasing. So for the Q sub S for segment number 1, and for the uniform or constant F, which is for Q sub S for segment number 2. Q sub S is equal to the summation of P times delta L times F for this method, and based on the diagram, the resistance is equal to Q sub S1 plus Q sub S2. So for segment 1, for Q sub S1, again we have our K and delta prime, an increasing F segment Z of about 0 to L prime, that is 6 meters. So for F, it is equal to K times sigma O prime times the tangent of delta prime. So for our Z, that is equal to 0, sigma O prime is equal to gamma times Z, wherein gamma is equal to 17.6. So times Z at Z, that is equal to 0, is 0. Thus our sigma O prime is equal to 0. So for our F at Z equal to 0, since our sigma O prime is 0, then our F is equal to 0. So at Z, that is equal to L prime, it is equal to 6 meters. Thus for our sigma sub L prime, that is about 6 meters prime, so it is equal to gamma prime times Z, wherein gamma is 17.6 kilonewtons per cubic meter times our Z, that is 6 meters. Thus the value is 105.6 kilopascals. So for our F, if we will now substitute our K, that is 1.3, our sigma O prime 105.6 kilopascals, and our tangent of delta prime, which is 0.8 of our P prime, that is 30 degrees, the F value is equal to 61.121 kilopascals. So for our F, for this increasing F segment, so that is for 0 to L prime, so get the average. So for our F of average, or F average, it is equal to F sub 0, which is 0, plus F sub L prime, which is 61.121 kilopascals. So the average of the two is equal to 30.560 kilopascals. Thus for our first component, so our QS sub 1, it is equal to the perimeter. So this is a square, therefore it is 4 times one side, which is 0.4 meter. So times our segment length, which is 6 meters. Then multiply that with our FAV, that is 30.56 kilonewtons per square meter. Thus, our first component is 293.381 kilonewtons. So for the updated unit friction, it will increase until L prime, that is 6 meters, to about 61.121 kilopascals, and it will be constant up to the tip of our footing. Thus, for segment number 2, at constant F segment, so that is Z of about L prime, 6 meters up to our L, 12 meters. Thus, our delta L sub 2 is 6 meters. So at Z, again for this segment, again F is constant, thus F is equal to 61.121 kilopascals. Therefore, for our second component, the QS2 is equal to P, again 4 times one side, so 0.4 meter, times our delta L2 for the segment length, which is 6 meters, times the F value, that is 61.121 kilonewtons per square meter. So for our QS2, it is equal to 586.762 kilonewtons. So for the total frictional resistance, so again, our QS1 plus QS2. So for QS1, that is 293.381 plus QS2, 586.762 kilonewtons. Thus, for our total frictional resistance, it is equal to 880.142 kilonewtons. So for Coyle and Castello's method, QS is equal to K times sigma O prime bar times the tangent of, we have our delta prime as 0.8 times P prime, then multiply it to P times L. So determine the embedment ratio, that is L all over D. So for our L, that is 12 meters divided by D of our side B, if that is square. But if this is circular, then that is the diameter. So for our case, for this problem, that is 0.4 meter. Thus, L all over D is equal to 30. So in figure 3.28, so with embedment ratio equal to 30, draw horizontal line. And identify the appropriate diagonal line for our P prime, which is 30 degrees. At the intersection, project through the logarithmic horizontal axis and identify the value of K as 0.4. So for the average overburden pressure, or the sigma O prime bar, at Z equal to 0, the sigma O prime is equal to gamma times Z. So at Z, that is 0, the sigma O prime is equal to 0. And at Z, that is at the end of the pile or tip, which is 12 meters. So we have our sigma prime 12 meters is equal to gamma, that is 17.6 times 12. It is equal to 211.2 kilopascals. Again, for this average overburden pressure, it is from extreme ends. So for the average value, the sigma O prime bar is equal to the sigma sub O prime and plus the sigma sub 12 meters prime, or that is the average of 0 and 211.2 kilopascals. And the average, therefore, is 105.6 kilopascals. Thus, for our Q sub S, it is equal to 0.4. So the K value times our sigma O prime bar, which is 105.6 kilonewtons per square meter, times the tangent of 0.8 then times phi prime, that is 30 degrees. Quantity, multiply these two, the perimeter. Again, we have a square with 4 sides times 0.4 meter each side. Then multiply to the total length, which is 12 meters. Thus, for our Q sub S, it is equal to 361.084 kilonewtons. So for the last requirement, which is the ultimate or Q sub U and the allowable or Q all load. So consider the average values of Q sub S according to the problem, or you may select the value which is lower, which means that it is more conservative. So for this example, Q sub S is equal to the average of QS for the first method, which is the general method, that is about 880.142 kilonewtons, and our QS for coil and Castello's method of about 361.084 kilonewtons. Thus, the average is 620.613 kilonewtons. So for the ultimate load capacity or Q sub U, this will be the sum of the two components. First is our point bearing capacity, which is Q sub P, plus our Q sub S, the skin frictional resistance. Thus, it is equal to our QP, 670.095 kilonewtons, so plus the QS, that is 620.613 kilonewtons. So therefore, for our ultimate load capacity, the Q sub U is equal to 1,290.708 kilonewtons. And for the allowable load or Q all is equal to the capacity divided by the factor of safety, or that is equal to 1,290.708 kilonewtons over our factor of safety, that is 3. Therefore, Q all is equal to 430.236 kilonewtons. So for our sample problem number 2, so this is problem 9.2 in page 497. So a 20-meter long concrete pile is shown in the figure. So estimate for letter A the frictional resistance for Q sub S using K, that is 1.5, and delta prime as 0.6 of P prime. For letter B, the frictional resistance Q sub S using coil and Castello's method. And for letter C, the ultimate and allowable load if the factor of safety is 3, and assume Q sub S is the average of requirements A and B. Assume that Q sub P is the average from our previous example. So this is actually the continuation of our problem from point bearing capacity. So for the general method, so K is equal to 1.5 and delta prime equal to 0.6 of P prime. So determine the depth wherein the unit skin friction, or F, is increasing and remains constant, that is at L prime measured from the ground level, wherein L prime is equal to 15 times D. So again, this is a square, therefore D is our side size. So that is 15 times D of 0.46 meter. Otherwise, our L prime is 6.9 meters. So with this value of L prime, that is 6.9 meters, we need to determine again the value of unit friction F, that is increasing for the Q sub S1 or for segment number 1, and for the uniform or constant F, that is for QS for segment number 2. And again, QS is equal to the sum of P times the delta L times F for general method. and the resistance is equal to the total of the components QS1 and QS2. So for segment number 1, for our Q sub S1, an increasing F segment that is for Z of about 0 from ground level to our L prime, which is 6.9 meters. So for this F is equal to K times sigma O prime times tangent of delta prime. So at the initial point, which is Z equal to 0, our sigma O prime is equal to gamma times Z, wherein Z is 0, thus sigma O prime is 0. So for the unit friction value, since sigma O prime is 0, the unit friction is also 0. So at Z equal to L prime, which is 6.9 meters, so our sigma L prime, which is 6.9 meters, is equal to gamma times Z, wherein gamma is 18.6 times Z, that is 6.9, or that is 128.34. And for our unit friction F at 6.9 meters, it is equal to K, that is 1.5 times sigma O prime, that is 128.34 kilopascals, times the tangent of delta prime of 0.6 times P prime. So for layers of soil, please do consider the property which is directly in contact to the skin of the pile. So for this problem, instead of 42, we will be using 30 degrees. Take note that if we are dealing with the point bearing, so we will consider the property at the tip of the footing. But if that is for skin friction, then we will use the property at the immediate side of the pile. Again, 30 degrees. Thus, for our unit friction, it is equal to 62.550 kilopascals. And for our F, for this increasing F segment, so we must obtain the average. So the average of 0 and 62.550 kilopascals, or that is 31.275 kilopascals. And using this FAV, multiply that to our perimeter, which is 4 sides of 0.46 meter times our initial segment length, that is delta L1, that is 6.9 meters. Our first component, or QS1, is equal to 397.069 kilonewtons. So for the updated unit friction, it will increase until the L prime, which is 6.9 meters, to about 62.550 kilopascals. And it will be constant until the tip of the pipe. So for segment number 2, so at constant F segment, that is at Z equal to L prime of 6.9 meters to L, the tip of the pile, of 20 meters. So for this zone now, again, F is constant with a value of 62.550 kilopascals as presented with our previous slide. So for our segment component QS, so it is equal to the perimeter, which is 4 sides of a square, that is 0.46 meter, multiply that to our segment length, 13.1 meters, then multiply to the constant F, which is 62.550 kilonewtons per square meter. Therefore, the component is 1,507.712 kilonewtons. So for the total frictional resistance, so we will now sum the two components. So QS1 is 397.069 kilonewtons. And our QS2, 1,507.712 kilonewtons. Thus, for our QS, it is equal to 1,904.781 kilonewtons. So, for Coyle and Castello's method, so determine the embedment ratio. So L for this problem is 20 meters while D is 0.46 meter. Thus, the value is 43.478, which is beyond already the range that is 36 embedment ratio value. Thus, to avoid error, so it is better if we will not consider this method. Thus, for our last requirement, so which is the ultimate Q sub U and allowable Q all load, so we will only consider the value of QS from the general method, which is 1,904.781 kilonewtons. So considering the average value of Q sub P from our discussion of point bearing capacity, or load capacity, Q sub P is equal to 5,001.294 plus 5,150.639 divided by 2, or Q sub P is equal to 5,075.967 kilonewtons. So the ultimate load is the sum of our two components, the point load and our frictional resistance. So for the point load, that is 5,075.967 kilonewtons plus QS, which is 1,904.781 kilonewtons. Thus, for our Q sub U, or the ultimate load, it is equal to 6,980.748 kilonewtons. And for the allowable load, Q all, so it is equal to the capacity, that is 6,980.748 kilonewtons over the factor of safety, that is 3. Thus, Q all is equal to 2,326.916 kilonewtons. So for our next discussion, we will consider the correlation with standard penetration test, or SPT, results of average unit frictional resistance, or FAB. So for Meyerhoff, he suggested for high displacement driven piles, FAB is equal to 0.02 times PA times N60 bar. On the other hand, for low displacement driven piles, the FAB is equal to 0.01 times PA times N60 bar. And according to the second method, which is for the study of Brod, he suggested, or they suggested, that FAB is about 0.224 times PA times N60 bar raised to 0.29, wherein for our N60 bar, it is the average value of standard penetration resistance, or the average of all N60 within the range of the pile length, that is from ground surface towards the pile tip. And for our PA, it is the atmospheric pressure, again 100 kilopascals for metric and 2,000 for PSF for English. And to determine the frictional resistance value, it is equal to the perimeter times length L times the unit frictional resistance average, or FF. So let's take our sample problems. So for problem number 1, following is the variation of N60 with depth in a granular soil deposit. A concrete pile that is 9 meters long, 460 millimeters by 460 millimeters in cross section. is driven into the sand and fully embedded in the sand. Estimate the value of Q sub U. For letter A, Meyerhoff's method, assume pile under high displacement driven pile, and Q sub P from our point bearing load capacity discussion is 1286.528 kilonewtons. On the other hand, for letter B, Broad's method, wherein QP from our discussion of point bearing load capacity is 1110.313 kilonewtons. So for the first process, we need to identify the value of our N60 bar. Again, it is the average value of the standard penetration resistance within the total length of pile. So for the total length of pile, that is 9 meters. Therefore, consider the average within the range. So for N60 from 0 to 9, we will consider the total of 4 plus 7 plus 9 plus 10 plus 16 plus 20 divided by how many N60s. So for this one, we will consider 6. Thus, our N60 bar is equal to 11. So for Meyerhoff's method, Q sub P, that is equal to 1286.528 kilonewtons. So for high displacement driven piles, again, as per Meyerhoff, F of is 0.02 times PA times N60 bar. And substitute PA, that is 100 kilopascals, and N60 bar, that is 11. F of therefore is 22 kilopascals. And for frictional resistance, if we will substitute this F of and multiply it to the perimeter, so we have 4 sides of a square, that is 0.46 times the total length, which is 9 meters. Thus, Q sub S is 364.32 kilonewtons. Applying now the sum of the two to determine the ultimate load, the value of our ultimate load is 1650.848 kilonewtons. On the other hand, for Broad's method, Q sub P, that is 1110.313 kilonewtons. For F of, again, it is approximately equal to 0.224 times PA, which is 100 kilopascals, times N60 bar, which is 11 raised to 0.29. So for F of, the value is 44.901 kilopascals. And if we will substitute this in the equation of frictional resistance, we will then multiply it to the perimeter. So again, we have 4 sides of a square, that is 0.46 meter. Then multiply it to the length, 9 meters. Thus, our frictional resistance is 743.554 kilonewtons. And for the ultimate load capacity, we will now take the sum of the two. Thus, the value is 1853.867 kilonewtons. So let's take, therefore, the second problem. So for problem number 2, consider a pile in a sandy soil deposit 10 meters long with a diameter of 0.45 meter. Following is the variation of standard penetration resistance values, or N60. So with that, estimate the value of Q sub S. So we are required only of what is the value of Q sub S. So for the first process, we need to identify the value of N60 bar. Again, N60 bar is the average value of standard penetration resistance within the total length of the pile. So the total length of the pile is 10 meters. So from 0 to 10, within the range, the average is We have 6 plus 7 plus 5 plus 8 plus 10 plus 10 divided by the total numbers. So we have 6. Therefore, N60 bar is 7.667. So for Meyerhoff's method, for high displacement driven piles, the F of is equal to 0.02 times PA, which is 100 kilopascals, times N60 bar of 7.667. Therefore, our F of is 15.333 kilopascals. For frictional resistance, if we will substitute our F of to the equation, we will then multiply it to the perimeter. So for the perimeter, this is already circle or circular in section. Therefore, the perimeter is pi times the diameter, which is 0.45 meter. And multiply this to the length, that is 10 meters. Therefore, for Q sub S, it is 216.770 kilonewtons. On the other hand, for the second method, so for broad method, for F of, it is about 0.224, multiply that to PA, that is 100 kilopascals, and multiply to N60 bar of 7.667 raised to 0.29. F of, therefore, is 40.437 kilopascals. And therefore, if we will substitute this to the equation of frictional resistance, we will multiply it to the perimeter, again, circle, so pi times the diameter, 0.45 meter, then times L, which is 10 meters. Therefore, Q sub S is 571.671 kilonewtons. So please consider this problem as your practice problem. Okay, so that's it for the pile foundations under frictional resistance Q sub S in sand. Take care and God bless.